Topic 5 of week 1 is various ways to represent a function. Specifically, we will look at 4 different ways to represent a function. And the first one, and by far the most important one, is representing functions analytically. Analytically means by a formula. By a formula. You're all familiar with this way of representing functions. The only thing I want to mention here is that when a function is given by a formula and domain is not given specifically, let's make it a convention. When a function is given by a formula, but the domain is not specifically given, we agree to understand that the domain is the set of all values for which the formula makes sense. We agree that the domain is the set of all numbers for which the formula makes sense. For example, if you're given the formula f of x equals x squared, but the domain is not specified, this formula makes sense for all real numbers, so the domain is, we assume by our convention that the domain is the entire set of real numbers. Or when our function is 1 over x, and again domain is not specified, we assume the domain is all the x's for which the formula makes sense, and of course it's just the set of real numbers minus the set containing 0. So all real numbers except 0, which you can also write as the union from negative infinity to 0, the interval from negative infinity to 0, union 0 to infinity. Functions could be added or multiplied, and the sum of two functions and the product of two functions naturally will be defined on the set that's the intersection of the domains of two functions being added or multiplied. So given two functions, let's say f and g, each with its own domain, we can define on the set which is the intersection of the two domains. We take domain of f and intersect it with domain of g and call that D, the sum of two functions, called and written f plus g, which is of course f applied to x plus g applied to x. And likewise the product. Which is of course just f applied to x times g applied to x. We can also define the quotient of these two functions, but that's a little trickier. You have to make sure that the denominator is not 0. Right, so whenever, or rather for all x in D for which g is not 0, we can define the quotient f divided by g, which is just f of x, or f applied to x divided by g applied to x. Again, here x is in D and g of x is not 0. Another thing I wanted to mention here is that occasionally we will have the situation when our function is defined explicitly. Occasionally we will define functions explicitly, or rather implicitly. We will define functions implicitly by equations involving x and y. Say, for example, the equation 2x plus 3y equals 7 is not explicit in y. It's not of the form y equals some function of x. But of course, we can easily solve this for y, and this equation defines y as a function of x. Is an equation which defines y as a function of x. All we really need to do is to solve this for y, and solving for y, we get the function negative 7 halves x plus 7 halves. Oops, that's not correct. It should be negative 7/3 plus 7/3. The thing to keep in mind here is that not every equation like this defines a function y of x. Not every equation involving x and y defines a function y of x. And let me write this down and let me give you an example. Not every equation of the form some f of xy equals 0 determines y, or defines, I should say defines, y as a function of x. Here is one example. If you consider the equation that I'm sure you know, x squared plus y squared equals 1, which is geometrically a circle. More formally, the set of points in the xy plane whose coordinates x and y satisfy this equation form a circle of radius 1 centered at the origin. which is geometrically a circle of radius 1 centered at the origin. But does this equation define y as a function of x? Well, the easiest way to see this, does this equation define y as a function of x? The easiest way to answer this question is to actually start solving for y. If we take this equation, x squared plus y squared equals 1, that's equivalent to y squared being equal to 1 minus x squared, which is equivalent to root of y squared being equal to root of 1 minus x squared, of course under the assumption that 1 minus x squared is non-negative. Right now, this is equivalent to, well, this inequality means x is between negative 1 and 1, and the equation turns into absolute value of y being equal to root 1 minus x squared. Right? Remember again, root of a squared is not a in general. Root of a squared is a, only when a is non-negative. If you want to write an equation for any real a, not necessarily positive or non-negative, you can't write that root of a squared equals a, because if a is negative, right, this becomes nonsense. Root of negative 1 squared equals negative 1. It cannot be, because square root is never negative. So what you want to write is absolute value, right? And that's a if a is positive or non-negative, and negative a if a is negative. So what I get here is y actually equals plus minus square root of 1 minus x squared when x is between negative 1 and 1. It is this plus or minus that makes this equation not define a function. Specifically, what happens is that if you fix on x, you actually get two functions. One is y equals positive square root of 1 minus x squared. Let me use another color here for x, not green maybe. One function is y equals positive root 1 minus x squared. That's the upper semicircle. And the other function is negative that. What color should I use? Let's use black. this point here has coordinates x comma negative root 1 minus x squared. So what I'm saying is that for every x in between negative 1 and 1, both pairs x comma positive root 1 minus x squared and x comma negative that satisfy the equation, or rather belong to the relation stemming from this equation. This equation certainly determines a relation where we say that x is related to y whenever x and y satisfy this equation. But this relation is not a function because the positive square root is in general not equal to the negative square root. Since in general the positive square root 1 minus x squared is not equal to the negative square root of 1 minus x squared, this relation is not a function. Remember, a function has to have the property that for every x there's exactly one y. For every x in the domain, right, there is exactly one y, or in other words, if y equals f of x and z equals f of x, then necessarily y equals z. That's not the case in our situation. We have an x and we have different y and z. I could think of this as y and of this as z, and clearly they're not equal. They're opposites of each other. They're not equal. And so this relation is not a function. Each of these, however, is a function. Square root of 1 minus x squared, defined on the interval negative 1, 1. And negative square root of 1 minus x squared, defined on the interval negative 1, 1. Certainly are functions. Now, also, I'd like to show you a couple of examples how to find the domains and images of functions given analytically. In this first example, we need to find the domain of the function square root of the fraction 2x plus 3 over x plus y plus square root x squared minus 2. Again, by our agreement, once the domain is not given, we take for the domain the largest set for which the formula makes sense. Right? So the square roots can only be taken of non-negative numbers, and the fraction only makes sense when the denominator is not 0. So we are solving the system 2x plus 3 over x plus 1 is non-negative, and x squared minus 2 is non-negative. Right? If we keep the first inequality the same and factor out the, rather, find the factorization for the other equation. Greater or equal than 0 for the other inequality, I mean. And now we find the related points on the number line. They will be, well, square root 2 and negative square root 2. And we need this to be greater or equal than 0. That happens when x is greater or equal than the largest root, or less or equal than the smallest root, negative square root 2. And now we also need to find the roots related to this fraction, negative 1 and negative 3/2. Negative 3/2 is here, and it could be included. And negative 1 is in between, and it must be excluded. Now, when is this fraction greater or equal than 0? This fraction is greater or equal than 0 either when both the numerator and denominator are positive, or both are negative. And we can easily find when this happens. Definitely when x is strictly greater than negative 1. They take 5, for instance. The numerator is positive and denominator is positive. In between the roots, say you can take negative 1.25. This number, 2x plus 3, will still be non-negative, or actually positive. But the denominator x plus 1 will be negative. So the ratio will be negative. And to the left of negative 3/2, we again get the fraction positive. So we find that the solution to this system simply is the union of two intervals from negative infinity to negative 3/2. Including negative 3/2, union the interval from root 2 to positive infinity. That is the domain of our function. Now, another example where the problem will be to find the image of a given function. Find the image of the function for x plus 8, x squared over x squared plus 5. Well, first of all, we clearly notice that the domain of the function . is the entire real line because the denominator is never 0. X squared plus 5 is never 0. Domain of f is the entire real line since x squared plus 5 is not 0 for any real x. So we are looking for all values of y for which we have this equation. If we equate this to y, have a solution for x. All values y and r for which the equation 4x plus 8 over x squared plus 5 equals y has a solution in x. Right, so we can view y as a parameter. Now, if we multiply both sides by x squared plus 5 to clear the denominator, clearing the denominator, we get y times x squared minus 4x plus 5y minus 8 equals 0, which is a quadratic equation in x if y is not 0. So if y is not 0, this here is a quadratic equation in x. And as we know, a quadratic equation has a solution if and only if the discriminant is non-negative. It has a solution if and only if the discriminant d, which is in this case a function of y, since y is a parameter in the equation. Remember, the discriminant is square of the coefficient in front of x in the first power minus 4 times the coefficient in front of x squared times the coefficient in front of x in the 0 power, or also known as the free term. 5y minus 8 is non-negative. So let me write this on the new page. We want the discriminant, which is negative 4 squared minus 4y, 5y minus 8 to be non-negative. Now, if we solve this inequality, what do we get? We get negative 20 y squared plus 32y plus 16 greater or equal than 0, or dividing everything by negative 4, not forgetting to flip the inequality. We have 5y squared minus 8y minus 4 less or equal than 0. And so I divided by negative 4. The roots of this quadratic are easy to find by a known formula. 64 minus 4 times 5 times negative 4. So what is under the square root? 4 times 4 is 16, 16 times 5 is 80, 80 plus 64 is 144, and 144 is the square of 12. And when you divide this by 2, you get 4 plus minus 6 over 5. So one root is therefore 4 plus 6 over 5, which is 2. And the other root is 4 minus 6 over 5, which is negative 2/5. And we need the parabola to be below the x-axis. So that'll be an interval between the roots, the interval between the roots. So that inequality is equivalent to y being between negative 2/5 and 2. And again, y is not 0. If y was 0, we need to look at that function, look at that equation separately. We want 4x plus 8 over x squared plus 2 to be equal to 0. Right? We have 4x plus 8 over x squared plus 5 equals 0. And that means x is negative 2. So 0 is also in the image of f. And we find finally that the image of f is the entire segment from negative 2/5 and 2. Right? Whenever y lies in this interval, the corresponding equation in x will have a solution. And that solution will be an element of the domain at which f will take value y. All right, so that example is finished. Another way to represent functions, aside from formulas, which we will use occasionally, is tables. Pretty simple idea. You would list values of the independent variable in one row, and then values of the dependent variable in another row. Or, of course, you can do this vertically. And here are a couple of examples. Actually, one example, I think. The question is asking, do the following tables define functions? The first table is this. The first row will be months in the year by number. That's the input or the independent variable. And the second row will be days in that month. Let's say D, that's the dependent variable. And the first row is, of course, numbers 1 through 12. And the other row is numbers 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, and 31. And we can easily see that this is indeed a table that defines D as a function of M. That is because for every value of M, we have one and only one value of D. And the second table is this. The first row will be age. That's the independent variable. And the second row will be height in inches at that age. The first row is 5, 5, 6, 7, 8, 9, 10. And the second row is 40, 42, 44, 47, 50, 52, and 54. And this time we see that H is not a function of A. That is because of the first two values of A. We would have to have H of 5 simultaneously 40 and 42. And of course, 40 and 42 are not equal. Even though this table does define a relation between A and H, we can say that 5 is related to 40 and 5 is related to 42, but we can't say that H is a function of A, because we have two pairs, 540 and 542, in which the same first coordinate is paired with two different second coordinates. This is not a function. All right. The third way to define a function is by a graph. And this is where we will talk about the vertical line test. Sometimes functions in this course will be determined by a graph. Let's look at some three examples, three graphs. This graph here actually is the graph of the function 2x plus 1. The second picture will look like this. Note that even though these are two pieces that don't share any points, this actually is the graph of one function. And the third picture. The graph looks like this. This here is the graph of a piecewise defined function. The function is defined differently for by different formulas for different values of the independent variable. It's 3x plus 1 whenever x is non-negative, and x plus 1 whenever x is negative. Piecewise defined function. We already know that we already saw examples that not every plane curve is the graph of some function. We already saw examples, let me remind you. Right? These are two curves, and we discussed in the past that this curve on the right cannot be the graph of a function because we have two pairs, a comma b and a comma c, on this graph, on this curve, with b being not equal to c. We formalize this observation in a theorem called the vertical line test, which establishes necessary and sufficient condition for a curve to be the graph of a function. The theorem is this: a curve, let's call it capital gamma, in the xy plane is the graph of a function y of x if and only if any vertical line that is any line parallel to the x-axis. Intersects gamma at most once. The proof is optional, and it's given in the PDF that will accompany this video lecture, but I can go back to that example and talk about how this theorem applies to this example. Let me copy it. So we can consider vertical lines crossing this curve in the left picture, right? And we see that no such curve, no such vertical line intersects the curve more than once. However, for the curve in the right picture, we can easily find vertical lines that intersect the curve more than once. That means the curve cannot be the graph of any function. Right? This line, this vertical line, intersects the graph more than once. I don't really need this. So this curve cannot be the graph of any function. Unlike here, any vertical line intersects this curve at most once. So this curve is the graph of a function. Okay. Now I want to show you an example where we find the domain and image of a function given graphically. So the example is this. Find the domain and image or range of the function whose graph is given. Let's say the function is f. And the graph is like this. So here is the excluded point. This value here, this point is included. This value here is 1. This value here is -3. And these two values here are -4. So by inspection, we can easily see that the domain of the function is the interval -3, 1, with 1 included, right, and -3 excluded. However, the image, right, that's along the y-axis. That's all the y values for which there exists an x such that y equals f of x, is the entire interval from -4 to 0 and all values in between. All horizontal lines from -4 to 0, including -4 and 0, intersect the curve at least once. And finally, the fourth way to represent a function, the least common, we sometimes represent functions by textual description. And let me give you an example here. So the function is this: for every real x, let f of x be the decimal approximation from below decimal approximation of x from below within 10 to the power -3. So for instance, f at square root 2 will be 1.414. F at pi will be 3.141. F at 41.4 will be 10/250. And f at -364/3 will be -121/334. I encourage you to think why the decimal approximation of square root 2, for instance, from below within 1/1000 is this. But this is a valid description of a function. It may be difficult to find a specific formula for this function f. Nonetheless, it is a function that is described in a textual way. You can actually find an explicit formula for this function f, and it's one of the exercises after this chapter. It's possible to find an explicit description for this function f. All right, that's it for various ways to represent functions.